Welcome. Tonight we embark on a different kind of prehistoric journey. We turn away from the familiar landscapes of lost continents, away from the shadows of giant beasts that walked the land. Instead, we dive deep into the planet's memory, seeking the stories held within the waters themselves. We journey into the forgotten oceans of prehistoric Earth. These are the vast, ancient seas that have long since vanished, their coastlines erased by drifting continents, their names known only to geology. We will travel back billions of years to the very first, perhaps boiling, oceans under a toxic sky. We will float through the strange microbial seas of the boring billion, explore the world beneath snowball Earth's ice, witness the closing of oceans that once separated continents, and glimpse the lost inland seas that divided lands we now know. It's a story of waters that birthed life, sheltered it through cataclysm, and then disappeared, leaving only faint, salty ghosts in the rock record. So, before you get comfortable, take a moment to like the video and subscribe. But only if you genuinely enjoy what I do here, and let me know in the comments where you're tuning in from and what time it is for you. It's always fascinating to see who is joining us from around the world. Now, dim the lights. Maybe turn on a fan for that soft background hum, perhaps like the faintest, deepest ocean current. And let's ease into tonight's journey together. Let's slip beneath the surface of time itself. When we think of the ocean, we picture the familiar blue expanse that covers 70% of our world today. The Pacific, the Atlantic, the Indian. They feel vast, eternal, almost unchanging in their ancient depths. But the oceans, like the lands they lap against, have a history far deeper, far stranger, and far more dynamic than we often imagine. Ocean basins are born, they grow, they shrink, and they die, swallowed by the slow, relentless engine of plate tectonics. The map of the world's waters has been constantly redrawn over the eons. Tonight we become hydropaleontologists, voyagers on these lost seas. We seek the character, the chemistry, the life, or lack thereof, within oceans that no longer exist. We begin our journey at the very beginning, in the turbulent infancy of our planet, when the first waters condensed upon a still-forming world, an ocean whose name is lost to time, perhaps because it existed before names themselves were conceivable. An ocean born of fire and steam. Our journey begins in the deepest abyss of time, an era so ancient it almost defies comprehension. We must travel back over 4 billion years to the very infancy of our planet, to the Hadean and early Archean eons. The names themselves evoke a sense of the infernal, Hades, the underworld, and for good reason. This was not the familiar blue and green marble we know. This was a planet still recovering from its violent birth, a world of fire, impact, and a sky thick with poison. Imagine a landscape utterly alien. The young Earth was still intensely hot, its surface perhaps largely molten or covered by a thin, unstable crust constantly being fractured and reshaped by immense volcanic eruptions. There were no continents as we know them, perhaps just scattered volcanic islands rising from a global magma ocean. And the sky offered no comfort. The atmosphere was a dense, suffocating shroud, composed not of breathable nitrogen and oxygen, but of carbon dioxide, water vapor, methane, ammonia, and sulfurous gases belched out from the planet's interior. It was a toxic, primordial soup, perhaps thick with volcanic smog, under a sun that, while younger and slightly dimmer than today, still delivered intense radiation unfiltered by any protective ozone layer. Adding to this chaos was a relentless cosmic bombardment. The young solar system was still a shooting gallery. Asteroids and comets, large and small, rained down upon the planet's surface with terrifying frequency, their impacts vaporizing rock, creating vast seas of lava and potentially boiling away any surface water that dared to accumulate. It was a world under siege from within and without. Yet, amidst this Hadean inferno, the seeds of the oceans were present. The water itself likely arrived early, perhaps delivered by those very comets and asteroids, or perhaps outgassed from the planet's interior along with the volcanic fumes. In the intense heat, this water existed primarily as steam, a colossal planet-enveloping greenhouse layer within that already thick atmosphere. But the Earth slowly, patiently began to cool. As the relentless bombardment lessened, as the first stable crust began to form, the planet's surface temperature eventually dropped below the boiling point of water. And then the rains began. Not a gentle shower, but perhaps a deluge of unimaginable scale and duration, raining down from that immense atmospheric reservoir of steam. Water poured from the sky, possibly for centuries, for millennia, cascading across the barren volcanic rock, pooling in the low-lying basins, filling the impact craters. The first oceans were born. But what were these primal oceans like? Forget the cool, blue, life-filled seas of today. These first waters were likely as alien and hostile as the world that contained them. Born from steam condensing on hot volcanic rock, they were probably hot, perhaps simmering close to boiling point in places, heated from below by the planet's residual heat and from above by the thick greenhouse atmosphere. Infused with volcanic gases like carbon dioxide and sulfur dioxide, they were almost certainly acidic, corrosive enough to rapidly weather the primordial rocks they touched, leaching minerals into the water. And they were likely rich in dissolved metals, particularly iron, washed out from the young planet's crust. With no free oxygen yet present to cause rust, this dissolved iron might have given the early oceans a strange, pale greenish hue, not the familiar blue derived from the scattering of sunlight in clear water. Think less of a tropical lagoon, more of a vast, simmering, mineral-laced chemical bath. There was, of course, virtually no free oxygen dissolved in these waters. Oxygen, the fuel of complex life, had not yet begun its slow accumulation. These were anoxic seas, suitable perhaps only for the hardiest, most primitive forms of anaerobic life, if life had even begun at all by this point. This was the cradle, not a gentle, nurturing pool, but a hot, acidic, metallic, breathless cauldron, a seemingly impossible environment, and yet it was within these turbulent, steaming, primordial waters, perhaps in the deep, dark places where chemical energy offered an alternative to the harsh surface, that the very first tentative whispers of biology might have begun to stir. The stage was set, not for a garden, but for a chemical miracle. These first hostile oceans, hot, acidic, metallic, and starved of oxygen, seem an unlikely cradle for the delicate beginnings of life. The surface, bombarded by meteorites and bathed in harsh ultraviolet radiation under a toxic sky, offered no sanctuary. Where then, in this seemingly impossible cauldron, could the intricate chemistry of biology have possibly gained its first fragile foothold? One of the most compelling answers leads away from the turbulent sunlit surface and down, deep down, into the crushing darkness of the abyssal floor. Here, even in the planet's infancy, the restless geology of the young Earth likely created unique and potentially life-giving oases, hydrothermal vents. The floor of this early Archean ocean presents a landscape of fresh, black volcanic rock, formed as the planet's crust cooled and solidified. This crust, however, was thin, unstable, riddled with cracks and fissures penetrating deep into the hot mantle below. Cold, dense seawater would have seeped down into these cracks, sometimes for miles. Descending into the Earth, this water was heated by intense geothermal energy. It reacted chemically with the hot rocks, becoming enriched with dissolved minerals and gases, methane, ammonia, hydrogen sulfide, metals like iron and nickel. This superheated, chemically charged fluid, now far hotter and more buoyant than the surrounding seawater, then rose rapidly back towards the surface, erupting from the seafloor through openings, the vents. These vents could manifest as towering chimney-like structures, built up slowly over time by minerals precipitating out of the hot fluid as it mixed with the cold, ambient seawater. These are the black smokers, belching plumes of dark, mineral-rich water into the abyss. Elsewhere, gentler, warmer seeps might release clear, alkaline fluids rich in hydrogen, the lost city-type vents. Around these oases of geothermal energy, a truly alien ecosystem could have formed, utterly independent of the sun. Here, in the crushing darkness, life would not be powered by photosynthesis, but by chemosynthesis. Primitive microorganisms, perhaps the very first cells, could have harnessed the chemical energy locked within the dissolved gases erupting from the vents: hydrogen sulfide, methane, hydrogen itself. They would have used this chemical energy to build their bodies, forming the base of a unique and self-contained food web. It was a world thriving in utter blackness, fueled not by light, but by the Earth's own internal heat and chemistry. Microbial mats might have formed around the vents, perhaps strange filaments of bacteria capturing the mineral-rich plumes. These microbes would have formed the foundation, potentially supporting slightly more complex, but still microscopic consumers. Why are these vents considered such a strong candidate for the cradle of life? They offer a unique convergence of conditions that primitive biology might have needed. They provide a sustained source of energy, chemical energy. They offer abundant raw materials, dissolved minerals and gases. The complex mineral structures of the vents themselves, riddled with tiny pores and compartments, could have acted as natural catalysts and scaffolding, concentrating organic molecules and providing protected microenvironments where the first delicate cells could assemble. And crucially, the deep ocean offered protection, shelter from the harsh UV radiation and constant meteorite impacts that plagued the surface world. Was this the place? Did the very first spark of life ignite here in the warm, dark, chemical-rich embrace of a deep-sea hydrothermal vent 4 billion years ago? Certainty remains elusive. The rock record from this immense depth of time is incredibly sparse, altered by heat and pressure, offering only the faintest, most ambiguous chemical hints. But the hypothesis remains powerful, compelling. It suggests life's beginning was not a sun-drenched miracle in a shallow pool, but a slow, dark, and almost geological process, emerging naturally from the planet's own restless chemistry in the deepest, most hidden corners of its first forgotten oceans. These hydrothermal vents, these oases of chemical energy, might represent the very first ecosystem, the silent, deep root from which the entire tree of life would eventually, slowly and patiently grow. The hydrothermal vents, those deep-sea oases crackling with geothermal energy, offer a compelling stage for life's first appearance, but the life that might have arisen here operated under a set of rules fundamentally different from the sun-drenched world we know. This was life without sun, an existence powered not by photons captured from the sky, but by the raw chemical energy welling up from the planet's own molten heart. Today, almost every ecosystem we see, from the tallest rainforest to the most vibrant coral reef, is ultimately fueled by photosynthesis. Plants and algae capture sunlight, converting its energy into sugars, forming the base of a food web that everything else depends upon. Light is the primary currency. But in the deep, dark abyss of the early Archean Ocean, sunlight was irrelevant. It simply did not reach. Here, life had to invent a different way. It had to learn to eat rock, to breathe chemicals. This process is chemosynthesis. Consider the waters erupting from a black smoke event. They are a rich, potent brew of dissolved chemicals: hydrogen sulfide, methane, hydrogen gas, iron, manganese. To the oxygen-breathing life of today, this mixture is largely toxic. But to the earliest, anaerobic microbes, it was a feast. Certain types of bacteria and archaea evolved the incredible biochemical machinery to harness the energy released when these chemicals reacted with other substances in the seawater, perhaps dissolved carbon dioxide or sulfate. They didn't need sunlight. They extracted energy directly from these inorganic reactions. It was like finding a way to run a car engine not on gasoline, but on the fumes from a volcanic vent. These chemosynthetic microbes became the primary producers of the vent ecosystem. They were the base of the food web, the equivalent of plants in this sunless world. They formed thick, slimy mats directly on the vent chimneys, or perhaps existed as free-floating clouds within the mineral-rich plumes. And upon this foundation, a simple ecosystem could potentially build. Other microbes might have evolved to consume the chemosynthesizers, becoming the first primary consumers. Perhaps even slightly more complex, but still microscopic, predators emerged, feeding on these consumers. It would have been a purely microbial food web, a silent, invisible dance of chemical energy exchange happening in the crushing darkness. This concept of life thriving entirely without sunlight was once considered scientific heresy. But the discovery of vibrant, complex ecosystems around modern hydrothermal vents in the late 1970s proved that chemosynthesis is not just a theoretical possibility. It is a powerful and enduring strategy for life. Today, these vents support bizarre tube worms, ghostly white crabs, and dense mats of bacteria, all fueled by the Earth's internal heat. Could the very first life on Earth have been one of these chemosynthetic microbes born in the protected, energy-rich environment of a deep-sea vent? It is a deeply compelling idea. It places life's origins not in a warm little pond under the sun, as Darwin once speculated, but in a dark, hot, and seemingly hostile abyss, intimately connected to the planet's own geological processes. Life born of chemosynthesis would have been perfectly adapted to the conditions of the early Earth, thriving in the absence of oxygen, potentially tolerant of high temperatures, and independent of the harsh, radiation-drenched surface. It would have been a hidden, subterranean beginning, a slow colonization of the planet's dark, wet niches, long before the surface world became truly habitable. Whether life began here or merely found refuge here, the deep sea vents represent a profound example of life's ingenuity, its ability to find energy and sustenance in the most unlikely of places. They are a window into a different kind of biology, a biology powered by the planet itself. And the legacy of this early sunless life, this chemical foundation, would subtly shape the future chemistry of the oceans for billions of years to come. We speak of these first oceans, these Hadean and Archean seas, with a sense of profound mystery, piecing together their likely chemistry and speculating about the life that might have flickered within their depths. But why is this era so deeply shrouded in uncertainty? Why are these first vast oceans, which covered the planet for perhaps 1 billion years, effectively forgotten by the geological record? Why do we have clearer pictures of life from the Cambrian 500 million years ago than we do from these even more ancient waters? The answer lies in the relentless, destructive and transformative power of geological time itself. The Earth is not a static museum, carefully preserving every chapter of its history. It is a dynamic, restless planet, constantly recycling its own crust, erasing the past in the very process of creating the future. The rocks that formed the floor of those earliest oceans, the very sediments that might have held the delicate fossils or chemical signatures of the first life, have endured an almost unimaginable journey. Over the intervening 4 billion years, they have been subjected to immense heat and pressure deep within the Earth's mantle. They have been squeezed, folded, melted, and recrystallized countless times as continents collided, mountains rose, and tectonic plates subducted back into the planet's fiery interior. This process, known as metamorphism, fundamentally alters the character of the rock. It is like taking a book and baking it in an oven until the pages fuse together and the ink runs, leaving behind only a charred, unreadable mass. The intense heat and pressure destroy the delicate structures of fossils, erasing the intricate details that paleontologists rely upon. They reset the chemical clocks that scientists use to date rocks. They scramble the subtle isotopic signatures that might hint at ancient biological processes. As a result, finding truly ancient, unaltered rocks from the Hadean and early Archean is incredibly rare. These pristine remnants exist only in a few precious locations around the globe. Places like Western Greenland, northwestern Canada, and Western Australia. Small, geological islands of ancient crust that have somehow, miraculously, escaped the full fury of the planet's recycling engine. And even within these rare ancient rocks, the evidence for the earliest life is often frustratingly ambiguous. We are not looking for bones or shells. Those did not yet exist. We are searching for far subtler clues. Perhaps microscopic filaments that might be fossilized bacteria, but could also be non-biological mineral growths. Perhaps unusual ratios of carbon isotopes preserved in ancient graphite, ratios that suggest biological activity, but could potentially be explained by non-living chemical processes. Perhaps tiny layered structures within the rock that resemble stromatolites, those microbial mats, but could also be formed by sedimentation or mineral precipitation. Each potential clue is intensely debated, scrutinized, challenged. Pushing back the definitive record of life requires extraordinary evidence, precisely because the processes of metamorphism can so easily mimic the very signatures we are looking for. This deep veil of geological alteration means that the first billion years of the ocean's history, the very time when life likely began and established its fundamental biochemistry, remains the most enigmatic chapter in our planet's story. We have compelling theories, like the hydrothermal vent hypothesis. We have suggestive chemical whispers. But we lack the clear, undeniable, fossilized narrative that illuminates later periods. These first oceans are forgotten, not because they were unimportant, but because the very processes that shape our planet have worked tirelessly to erase their memory. We are left searching for ghosts in metamorphosed stone, piecing together a story from the faintest, most distorted of echoes. Yet, even these echoes suggest that the life born in these turbulent waters, however fragile, was already beginning to alter the chemistry of the planet, setting the stage for all that would follow. And so, even without a clear fossil record, the legacy of these ancient waters endures. The Hadean and Archean oceans remain shrouded in a deep geological fog, but they were far from insignificant. They were the crucible, the first great chemical laboratory of Earth. Within their hidden depths, geological and perhaps even biological processes began writing the planet's first and most enduring script, the blueprint for all future oceans. Perhaps the most significant aspect of this legacy relates back to the very composition of those early waters. As we've pictured, they were likely anoxic, devoid of free oxygen, and rich in dissolved iron, leached from the young planet's crust. For hundreds of millions of years, this iron-rich state defined the ocean's chemistry. But somewhere amidst this ancient greenish water, likely towards the end of the Archean Eon, the single most important biochemical innovation in Earth's history occurred: oxygenic photosynthesis. Cyanobacteria, those remarkable microbes, evolved the ability to harness sunlight, split water, and release oxygen. This was a biological revolution, but its initial impact was not felt in the atmosphere. It was felt within the ocean itself. The oxygen produced by these early photosynthesizers did not simply bubble away into the sky. It immediately encountered the vast reservoir of dissolved iron. A great planetary rusting began. The newly produced oxygen reacted chemically with the dissolved iron, causing it to precipitate out of the water column as solid iron oxides, essentially rust particles. These particles then rained down onto the seafloor, accumulating in thick layers. Over millions of years, interspersed perhaps with layers of silica-rich sediment, this process created the spectacular geological formations known today as banded iron formations BIFS. These immense deposits found in ancient Archean and early Proterozoic rocks around the world are the primary source of the iron ore that fuels our modern civilization. They are, in essence, the fossilized rust of the early Earth, a direct chemical signature of the moment when life first began to breathe oxygen into the world. This great rusting event was a crucial step. It acted as a planetary oxygen sink, consuming the oxygen produced by early life and preventing it for a very long time from building up to significant levels in the atmosphere or even in the wider ocean. The ocean had to rust completely before the air could truly begin to change. But in locking away that immense quantity of iron, this process also cleared the way. Once the dissolved iron was largely removed from the seawater, the oxygen produced by the ever-evolving cyanobacteria could finally begin to accumulate, first in the surface waters and eventually seeping into the atmosphere above. The chemical stage was being set for the great oxidation event that would mark the beginning of the next great eon, the Proterozoic. Beyond oxygen and iron, these earliest oceans were also the birthplace of the fundamental biogeochemical cycles that govern our planet. Early microbial life, even in the absence of oxygen, likely established the basic cycles of carbon, nitrogen, sulfur, and phosphorus. They learned how to fix nitrogen from the water, how to cycle carbon through fermentation and methanogenesis, how to utilize sulfur compounds for energy. These intricate, microscopic chemical pathways, forged in the Archean seas, created the underlying biochemical operating system upon which all future, more complex ecosystems would depend. So, while the Hadean and Archean oceans remain forgotten, in the sense that their direct physical remnants are scarce, their influence is profound and enduring. They were not a static prelude, but an active, transformative phase. They established the chemical conditions, precipitated the mineral resources, and perhaps even hosted the very origin of life itself. They were the necessary, fiery, and turbulent first draft, the chemical crucible that forged the potential for the vastly different and perhaps deceptively quieter oceans of the long eon that was about to dawn. Our journey now takes us out of the fiery, tumultuous infancy of the planet and into Earth's long, quiet adolescence. We enter the Proterozoic Eon, a vast stretch of time lasting nearly 2 billion years, from roughly 2.5 billion years ago down to the cusp of the Cambrian explosion at 541 million years ago. Within this immense eon lies a period often referred to, perhaps unfairly, as the boring billion. A seemingly endless interval where the pace of evolutionary change appeared to slow to a crawl, and the oceans settled into a state of profound microbial stability. The world is transforming, but slowly. The intense meteorite bombardment of the Hadean is a distant memory. The atmosphere, thanks to the persistent work of the cyanobacteria and the great rusting of the Archean seas, now contains a small but significant amount of free oxygen, perhaps a few % of modern levels. This oxygen would have begun to form a nascent ozone layer high in the stratosphere, offering the planet's surface its first tentative shield against the harshest solar radiation. The continents, no longer scattered volcanic islands, have grown, collided and coalesced into larger, more stable landmasses. Plate tectonics are in full swing, driving the slow dance of continental drift. And the oceans, They are vast, global, and outwardly, perhaps deceptively, calm. The extreme heat and acidity of the Archean seas have likely subsided, replaced by waters that are cooler, clearer, and chemically closer to those we know today, though still fundamentally different in their oxygenation and perhaps nutrient levels. Yet, despite these changes, despite the presence of oxygen and the emergence of the first complex eukaryotic cells with a nucleus, the great leap into macroscopic animal life remained stubbornly elusive for much of this eon. The oceans, for 1 billion years or more, seem to have remained firmly under the dominion of the microbial kingdom. It is a world difficult to truly grasp. Imagine an ocean stretching across millennia, superficially resembling our own in its vastness and blue hue, yet fundamentally simpler, quieter, operating at a slower microbial rhythm. It was a world ruled by the invisible, a planet where the most significant ecological dramas were playing out at the scale of single cells in the silent chemical exchanges within vast, slimy mats. This apparent stasis, this boringness, is one of the great puzzles in the history of life. Why did evolution seem to pause? What held back the explosion of complexity that seemed so imminent? To understand this forgotten ocean, we must delve into its unique character, its dominant life forms, and the vast planetary stage upon which this long, quiet act unfolded. The world of the first true supercontinent and its encompassing global sea. Central to the story of this long, quiet Proterozoic eon is the concept of the supercontinent. We saw Pangaea briefly in our earlier tales, that single landmass defining the end of the Paleozoic. But Pangaea was not the first time Earth's continents had gathered together. It was merely the most recent act in a slow, cyclical, planetary waltz. Deep within the heart of the boring billion, perhaps around 1.1 billion years ago, most of the planet's continental crust coalesced into another, even more ancient and far more enigmatic supercontinent, Rodinia. The name Rodinia comes from a Russian word meaning to give birth or motherland, reflecting its status as the ancestral core from which later continents would break apart. Piecing together its exact shape and position is a geological puzzle of immense difficulty, relying on subtle clues in ancient mountain belts and paleomagnetic data locked within billion-year-old rocks. But the general picture is one of a vast, sprawling landmass, perhaps centered near the equator, though its exact latitude remains debated. Imagine the core of ancient North America, Laurentia, sitting at the heart of this assembly. Attached to its sides are the ancient crustal blocks that would one day become Antarctica, Australia, Siberia, Baltica, Northern Europe, and perhaps parts of South America and Africa. It was a colossal jigsaw puzzle assembled by the slow, irresistible forces of plate tectonics. The interior of Rodinia, like Pangaea later, was likely a vast, arid expanse, far removed from the moderating influence of the ocean. Great mountain ranges, perhaps formed during the very collisions that assembled the supercontinent, might have dissected its surface. It was a stark, ancient landscape, perhaps largely barren, or maybe coated in places by the tenacious microbial crusts that constituted the only life on land. And surrounding this immense unified landmass was an equally immense unified ocean. If Rodinia was the motherland, this was the mother ocean, the vast, planet-encircling sea that filled the rest of the globe. Geologists call it Mirovia, from a Russian word meaning global. Morovia was likely the largest single ocean the Earth has seen since the very earliest days of water accumulating on the planet. It was the precursor to the later Panthallassic Ocean that surrounded Pangaea, and ultimately the ancestor of our modern Pacific. What was Morovia like? Its sheer size would have dictated its character. Imagine an ocean stretching, unbroken, across perhaps 2/3 of the planet's surface, Global ocean currents, unimpeded by scattered continents, might have flowed in vast, slow gyres, distributing heat or cold across the globe. Its chemistry was likely still evolving. While the surface waters, bathed in sunlight, were likely oxygenated by the tireless work of cyanobacteria, the deep abyss of Mirovia may have remained largely anoxic, perhaps even euxinic, sulfidic, a chemical remnant of the earlier Archean seas. This vast, oxygen-poor deep ocean could have acted as a significant barrier to the evolution and spread of early complex life, confining it perhaps to the shallow, oxygenated fringes around Rodinia. The shorelines of Mirovia, lapping against the edges of Rodinia, were likely the primary stage for biological activity. Here, in the shallow, sunlit waters, microbial mats would have flourished, building those characteristic stromatolite structures. This was the vibrant, productive fringe of an otherwise quiet, perhaps chemically stratified, global sea. Rodinia and Mirovia, a forgotten supercontinent and its encompassing, forgotten superocean. They defined the geography of our planet for perhaps 300 to 400 million years, a vast span of time during the heart of the Proterozoic. Their existence shaped the global climate, influenced ocean chemistry, and provided the grand, stable, yet perhaps restrictive stage upon which life existed during the long, slow, boring billion. They are ghosts on the map of deep time, their outlines traced only by the faintest geological clues, silent witnesses to an age when the world seemed locked in a state of profound microbial stillness. While the supercontinent Rodinia sprawled vast and perhaps largely barren across one hemisphere, the true heart of Proterozoic life pulsed within the shallow sunlit margins of the great Morovia ocean. Here, along coastlines bathed in ancient sunlight, life built structures, cities even, visible to the naked eye, monuments not of animal architects, but of the silent, persistent, and utterly dominant microbial kingdom. The seafloor of these Proterozoic shallows presented a landscape unlike anything widespread today. Instead of sandy bottoms churned by worms or coral reefs teeming with fish, vast areas were covered by thick, cohesive microbial mats. These living carpets, woven from cyanobacteria and countless other microorganisms, were the undisputed rulers of the coastal realm. They formed a tough, leathery, often colourful skin over the sediment, perhaps shades of deep green, reddish brown, or even black. And these mats were not just passive coverings, they were active builders. In areas where conditions were right, perhaps sheltered lagoons or tidal flats, these microbial communities engaged in a slow, patient form of geological artistry, constructing layered, dome-shaped, or columnar structures known as stromatolites. The process was simple, yet profound. The sticky surface of the microbial mat would trap fine particles of sediment, grains of sand, flakes of carbonate mud, washing over it with the tides or currents. The microbes, needing sunlight, would then grow upwards through this thin dusting of sediment, forming a new living layer on top. This new layer would, in turn, trap more sediment. Repeat this process day after day, year after year, millennium after millennium, and the result is a slow, upward growth, creating laminated, stony structures that can range from small, fist-sized domes to colossal columns several meters high. These were the stromatolite reefs, the great cities built by bacteria. During the Proterozoic, particularly in the heart of the boring billion, these structures reached their absolute peak of abundance and diversity. Imagine vast underwater landscapes dominated by these strange living rocks, fields of rounded cabbage-like domes, pillars reaching towards the sunlit surface, intricate branching forms creating complex, shallow water labyrinths. These stromatolite reefs were the ecological hubs of the Proterozoic ocean. They created topography on an otherwise flat sea floor. They provided surfaces for other microbes to colonize. They created sheltered microhabitats. And crucially, the photosynthetic cyanobacteria within them continued their tireless work, pumping oxygen into the shallow waters. Oxygen that was essential for the evolution of the first complex eukaryotic cells that were beginning to emerge and diversify in this microbial world. Around the ancient core of the Siberian craton, which formed part of Rodinia, shallow seas that might represent precursors to a distinct Siberian ocean likely hosted similar scenes, vast coastlines dominated by these microbial architects. The global reach of stromatolites during this era underscores the profound stability and uniformity of the marine ecosystems. To swim through these Proterozoic shallows would be to visit a world both incredibly simple and strangely architectural. It lacked the darting movement and complex interactions of a modern reef, yet possessed a silent geological grandeur. It was the peak expression of microbial power, a testament to a time when single-celled life, through sheer persistence and collective action, could build structures on the scale of landscapes. These stromatolite cities endured for over 1 billion years, the silent, dominant feature of Earth's oceans. Their slow decline would only begin much later, with the rise of the first grazing animals in the Ediacaran and Cambrian, creatures that learned to pierce and consume the microbial mats, disrupting the ancient process of stromatolite construction forever. But here, in the heart of the Proterozoic, their reign was absolute. They were the visible monuments of an invisible kingdom, patiently shaping their world layer by painstaking layer. And within the water column surrounding them, a slow chemical drama involving oxygen continued its fitful, uncertain course. While the microbial architects patiently constructed their stromatolite cities in the sunlit shallows of Mirovia and other Proterozoic seas, a far larger, less visible and profoundly important drama was unfolding within the water column and the atmosphere above. This was the story of oxygen, the volatile byproduct of photosynthesis, and its long, slow, and perhaps surprisingly turbulent journey towards becoming a dominant force in the planet's chemistry. The Great Oxidation Event, triggered billions of years earlier by the cyanobacteria, had marked a fundamental shift. It had rusted the oceans, clearing them of dissolved iron, and allowed free oxygen to begin accumulating, albeit slowly, in the atmosphere and surface waters. One might assume that from this point forward, oxygen levels simply climbed steadily upwards, paving a smooth, inevitable path towards the breathable air we know today. But the geological and chemical records from the Proterozoic Eon tell a more complex and far less certain story. The rise of oxygen was likely not a smooth, linear ascent. It was probably a fitful, fluctuating affair, perhaps characterized by long periods of relative stability at low levels, punctuated by temporary rises and even significant crashes. The atmosphere, it seems, was unstable, searching for a new equilibrium. What forces governed this oceanic and atmospheric oxygen budget? It was a delicate planetary-scale balancing act. On one side, the producers, the cyanobacteria, and later the first simple eukaryotic algae, tirelessly photosynthesizing in the sunlit surface waters, releasing oxygen. Their productivity was likely limited by the availability of essential nutrients, particularly phosphorus and trace metals, which might have been scarce in the Proterozoic oceans. On the other side, the consumers, the vast array of microbes engaged in decomposition, consuming organic matter and, in the process, consuming oxygen. The balance between how much organic carbon was produced and how much of it was buried in sediments, taking it out of the system, versus how much of it was not, was decomposed, using up oxygen, was likely a key factor controlling atmospheric O2 levels. Geological processes also played a crucial role. Volcanic outgassing continued to release reducing gases like methane and hydrogen sulfide that would react with and consume free oxygen. The weathering of rocks on land, influenced by the position of continents like Rodinia and the prevailing climate, could also impact nutrient runoff into the oceans, further influencing biological productivity and oxygen levels. The result of this complex interplay seems to have been an ocean and atmosphere where oxygen remained, for much of the boring billion, at levels significantly lower than today. Estimates vary widely, but perhaps atmospheric oxygen hovered at only 1 to 10% of modern levels for vast stretches of this eon, and the oceans themselves were likely chemically stratified. Imagine a relatively thin, oxygenated layer at the surface, perhaps extending down only a few tens or hundreds of meters, where photosynthetic life thrived. But beneath this oxygenated skin, the vast, deep abyss of Mirovia likely remained largely anoxic, perhaps even euxinic, sulfidic, a dark, poisonous realm, hostile to the oxygen-breathing eukaryotes that were beginning to evolve. This chemical stratification would have acted as another profound barrier, confining complex life to the shallow fringes, preventing its expansion into the deep sea. This persistent, widespread oxygen scarcity is considered by many scientists to be one of the primary reasons for the apparent evolutionary slowdown of the boring billion. Building large, complex, multicellular bodies, especially active, mobile animals, requires a high-energy metabolism fueled by abundant oxygen. Perhaps the planet simply couldn't provide enough of this vital fuel for much of the Proterozoic. Life had cracked the secret of eukaryotic complexity, but it was idling, waiting for the atmospheric and oceanic conditions to become truly favorable for the next great leap. The Proterozoic ocean, then, was not just a world ruled by microbes, it was a world fundamentally shaped and perhaps limited by the chemistry of oxygen. Its waters held the key to the future, but for a billion years, that key seemed stuck, unable to fully turn the lock that would unleash the animal kingdom. The name itself, the boring billion, carries a heavy weight of judgment. It paints a picture of a billion years of Earth's history as a time when nothing much happened, a dull, stagnant interlude between the dramatic origin of life and the explosive arrival of animals. But was this vast stretch of the Proterozoic ocean truly boring? Or is our perception colored by our bias towards the large, the fast, the complex, the things that leave behind obvious, spectacular fossils? From the perspective of a geologist measuring mountain building or continental drift, perhaps the pace was slower compared to other eras. From the perspective of a paleontologist searching for bones and shells, the fossil record is undeniably subtle. But from the perspective of life itself, particularly life at the cellular and biochemical level, this eon may have been anything but boring. It might have been a time of profound, albeit hidden, innovation, a slow, quiet, internal revolution that laid the essential groundwork for everything that followed. Why the apparent slowdown in macroevolution, the evolution of large, complex forms? As we touched upon, the persistently low oxygen levels remain the prime suspect. Building and sustaining a large multicellular body requires immense energy, and oxygen is the most efficient fuel source. Without abundant oxygen saturating the oceans, perhaps the metabolic cost of complexity was simply too high. Life was energetically constrained, confined to smaller sizes and simpler structures. The evolutionary engine was present, but the fuel line was restricted. Linked to this is the potential scarcity of essential nutrients. Trace metals like molybdenum, copper, and zinc are vital components of the enzymes needed for complex biological processes, including those involved in nitrogen cycling and building cellular structures. Some geochemical evidence suggests these trace metals may have been locked away in the deep sulfidic ocean waters for much of the Proterozoic, limiting their availability to life in the sunlit surface layers. Life might have possessed the genetic potential for greater complexity, but lacked the specific, crucial building blocks. It was like trying to build a complex machine with only the most basic, raw materials. The very stability of the environment could also have played a role. While stability sounds beneficial, evolution is often driven by change, by stress, by the need to adapt to new challenges. The long reign of the Rodinia supercontinent and the potentially stable, stratified Mirovia ocean might have created a world that was too stable. Without significant environmental pressure, perhaps the evolutionary drive towards radical new forms was simply weaker. Life had found a successful, stable equilibrium dominated by microbial mats and simple eukaryotes, and there was little incentive to disrupt it. And within the realm of genetics and development, crucial innovations may have been slowly, painstakingly accumulating. The evolution of sexual reproduction, which dramatically increases genetic variation and speeds up adaptation, became widespread during the Proterozoic. The complex genetic toolkit required for multicellularity, genes for cell adhesion, allowing cells to stick together, cell communication, allowing cells to communicate, cells to coordinate, and cell differentiation, allowing cells to specialize into tissues, was likely being assembled, piece by piece, within the genomes of single-celled eukaryotes and simple colonial forms. This was the invisible internal work, the writing of the complex instruction manual needed before complex bodies could actually be built. So perhaps the boring billion was not boring at all. Perhaps it was simply cryptic. A time when the most profound evolutionary action was happening at the microscopic and molecular level, hidden from the view afforded by the traditional fossil record. It was a time of essential preparation, of building the foundations, of assembling the toolkit. The ocean was not stagnant, it was simmering, it was patiently accumulating the potential energy, chemical, genetic, ecological, that would eventually fuel the great biological revolutions to come, starting with the dramatic deep freeze that would shatter this long, quiet equilibrium. This long, seemingly quiet Proterozoic eon, this boring billion, was far from a sterile waiting room. Beneath the surface calm of the Morovia ocean, within the microscopic bustle of the Stromatolite cities and the invisible world of plankton, the essential seeds of future complexity were being sown. The ocean was not truly stagnant, it was accumulating potential, patiently assembling the biological machinery that would underpin the explosion of forms to come. Crucial developments were unfolding at the cellular level. The eukaryotic cell, with its complex internal architecture, the nucleus housing the genetic material, the mitochondria acting as power plants, and in some lineages, the chloroplasts harnessing sunlight, had already emerged from simpler prokaryotic ancestors. Throughout the Proterozoic, these eukaryotes diversified, experimenting with different internal structures, metabolic pathways, and ways of interacting with their environment. This was the quiet internal arms race, happening within the cell walls, refining the very engine of complex life. Perhaps the most significant innovation within this eukaryotic realm was the widespread adoption of sexual reproduction. While simpler forms of genetic exchange existed before, the evolution of meiosis and the fusion of gametes, the fundamental process of sex, became common during the Proterozoic. This was a revolutionary development. Sexual reproduction shuffles the genetic deck with every generation, creating novel combinations of traits, vastly increasing variation within populations. This variation is the raw material upon which natural selection acts. Sex turbocharged the engine of evolution, dramatically increasing the potential for adaptation and the exploration of new biological possibilities. The quiet billion may have been the time when life learned how to truly innovate genetically. And the first tentative steps towards multicellularity were being taken. Simple colonies, where individual eukaryotic cells lived together, perhaps cooperating in rudimentary ways, became more common. The genetic pathways for cells to adhere to one another, to communicate through chemical signals, and even to specialize into different roles within a colony, were likely being laid down. These were not yet true animals or plants with complex tissues and organs, but they were the crucial intermediate steps, the evolutionary experiments testing the waters of cooperation. Imagine simple filaments of algal cells or spherical colonies like volvox hovering in the water column, precursors to the integrated bodies of the future. Even the environment itself, though perhaps stable for long stretches, was subtly changing. The slow, relentless work of the cyanobacteria continued to pump oxygen into the system, however fitfully. Geochemical cycles, driven by plate tectonics and microbial activity, continued to alter the composition of the oceans and atmosphere. Nutrients might have accumulated slowly in certain regions. The stage was being subtly, incrementally prepared. So, when we look back at the Proterozoic ocean, we should see it not as a period of evolutionary failure, but as a period of profound, albeit hidden, preparation. It was the long, slow inhale before the great evolutionary exhale. It was the time spent forging the tools, writing the genetic code, and establishing the cellular machinery. The billion years were not boring, they were essential. They built the unseen foundation. And this long period of quiet accumulation, this slow build-up of biological potential, made the subsequent changes all the more dramatic. When the environmental conditions finally shifted, when the long stability was shattered by the immense global trauma of the snowball Earth glaciations, life was, perhaps for the first time, truly ready to respond in a new and spectacular way. The seeds sown in the quiet billion were about to germinate in the dramatic thaw that followed. The long, quiet stability of the boring billion, the era dominated by the Rodinia supercontinent and the vast Mirovia ocean, was not destined to last forever. Around 720 million years ago, the Earth plunged into a period of climatic chaos unlike anything it had experienced before or since. The planet's thermostat didn't just dip, it plummeted. This was the beginning of the Cryogenian period, the age of snowball Earth. The concept itself is almost unimaginable, a scenario plucked from science fiction. It proposes that for tens of millions of years, not once but perhaps multiple times, the entire planet, or very nearly the entire planet, became encased in a thick shell of ice. What could trigger such a profound global deep freeze? The exact causes are still debated, a complex interplay of geological and atmospheric factors. The breakup of the Rodinia supercontinent, which began around this time, may have played a crucial role. As Rodinia fragmented, it created new coastlines, increased rainfall, and accelerated the process of rock weathering. This weathering pulls carbon dioxide (CO2) out of the atmosphere. If this drawdown of CO2 became too efficient, it could have weakened the planet's natural greenhouse effect, tipping the climate into a runaway ice age. Another factor might have been the position of the continents. If most of the land masses were clustered in the tropics, as some reconstructions suggest, this might paradoxically make glaciation easier. Tropical land weathers faster, pulling down CO2 more effectively. And once ice sheets began to form at the poles, a powerful feedback loop kicked in. Ice is highly reflective. It bounces sunlight back into space. As the ice sheets expanded, they reflected more sunlight, further cooling the planet, allowing the ice to expand even further. This ice albedo feedback could have rapidly pushed the Earth past a tipping point, allowing the glaciers to surge outwards from the poles, potentially meeting at the equator itself. Imagine the planet transforming. Glaciers, miles thick, grind their way across the continents, scraping the rock bare. Sea levels plummet as vast amounts of water are locked up in the ice sheets, and the oceans themselves begin to freeze over, first at the poles, then relentlessly creeping towards the tropics, until perhaps only a thin sliver of open water, or maybe just slush, remains at the very equator, or perhaps even that disappears, leaving the entire planet a ghostly white snowball, reflecting the faint sunlight back into the cold void of space. This was not a gentle winter. It was a planetary cryogenian nightmare, a deep freeze that persisted for millions of years. It represents one of the most extreme environmental challenges life on Earth has ever faced. The vibrant, sunlit, shallow seas of the Proterozoic, those bustling Stromatolite cities, were gone, buried beneath an impenetrable crust of ice, perhaps kilometers thick. Life, which had spent 1 billion years diversifying in those quiet waters, was suddenly facing near total annihilation. The vast majority of its familiar habitat simply ceased to exist. Where could it possibly go? How could anything survive on a planet that had become a solid ball of ice? The oceans, once the cradle of life, were now seemingly frozen tombs. But even beneath the ice, in the crushing darkness, faint pockets of warmth, and perhaps even life, may have endured. The snowball Earth had descended. Glaciers miles thick entombed the continents, and a vast, perhaps unbroken sheet of ice sealed the oceans beneath a frozen roof. What became of the great Morovia Ocean, that globe-spanning sea that had surrounded the Rodinia supercontinent for hundreds of millions of years? And what happened within the newer, smaller ocean basins that were just beginning to form as Rodinia started to break apart? The freezing of the oceans would have been a slow, inexorable process, likely beginning at the poles and creeping inwards. Imagine the surface waters chilling, sea ice forming, thickening, merging, until a solid crust locked the liquid world below away from the sky, away from the sun. This ice layer itself might have become incredibly thick, perhaps hundreds or even thousands of meters deep in places. Beneath this immense icy ceiling, the ocean transformed into a realm unlike any other in Earth's history. It was a world of profound darkness. Sunlight, the engine of almost all surface life, could not penetrate the thick ice shield, except perhaps in the thinnest equatorial regions. Photosynthesis, the foundation of the marine food web, would have largely shut down, plunging the waters into a state of perpetual night. It was a world of intense pressure. The sheer weight of the overlying ice added another layer of crushing pressure to the already immense pressures of the deep sea. And it was likely a world starved of oxygen, at least in large parts. Sealed off from the atmosphere, the ocean's oxygen supply, already perhaps low, could not be replenished. Any remaining oxygen would have been slowly consumed by the respiration of the few surviving organisms and by chemical reactions with minerals. Vast portions of the ocean beneath the ice likely became completely anoxic, perhaps even returning to the euxinic, sulfur-rich state of the much earlier Archean seas. Did the great Mirovia Ocean, the vast sea surrounding Rodinia, simply freeze solid? Or did it persist as a dark, cold, breathless body of liquid water trapped beneath the ice? It likely persisted as liquid, but in a state profoundly altered. And what of the newer oceans forming as Rodinia fragmented? The breakup of the supercontinent was creating new rift valleys, new coastlines, new basins that would eventually become the oceans separating the future continents. Basins like the Adamastor Ocean, opening between South America and Africa, the Mozambique Ocean, between Africa, Antarctica and Madagascar, and the Ferucian Ocean within Africa. These nascent oceans, born during a time of global refrigeration, would have spent their infancy trapped beneath the ice, their chemistry and potential for life shaped by these extreme conditions. Even the early precursors of the mighty Panthallassic Ocean, the ancestor of the Pacific, beginning to open as continents rifted apart, would have felt the icy grip. Life, faced with this global deep freeze and the transformation of its aquatic home, had only two options: adapt or perish. The vast majority likely perished. The sunlit shallow water ecosystems, the stromatolite reefs, the early eukaryotic plankton, these were likely devastated, their habitats either frozen solid or plunged into darkness. But life is tenacious. Where could it possibly have survived in this frozen ocean world? Where were the hidden refuges, the oases beneath the ice? The image of a planet entirely encased in ice paints a picture of utter desolation, a world seemingly hostile to any form of life. Yet, the very fact that complex life did re-emerge after the snowball Earth events tells us that survival, somehow, somewhere, was possible. The frozen oceans, while largely inhospitable, likely concealed hidden pockets, improbable sanctuaries where the flickering flame of eukaryotic life managed to endure the long, icy night. Identifying these potential refuges is key to understanding how life bridged this extreme glacial period. One compelling possibility lies, once again, in the deep ocean, near sources of geothermal heat. Hydrothermal vents, those oases of chemical energy we explored in the earliest Archean seas, would have continued to pump hot, mineral-rich fluids from the Earth's interior, regardless of the icy conditions far above. Around these vents, areas of liquid water would have persisted, warmed from below. Here, in the perpetual darkness, chemosynthetic microbes, bacteria and archaea feeding on sulfur compounds or methane could have continued to thrive, forming the base of a simple, localized food web. Could these deep, dark, warm pockets have also sheltered the first simple eukaryotic life forms, perhaps primitive fungi or protists, allowing them to ride out the glaciation in a state of suspended animation or slow, chemically fueled existence? It's a plausible scenario, life clinging to the planet's internal warmth while the surface froze. Another potential refuge lies at the opposite extreme, the surface itself, but only under very specific conditions. Even on a snowball Earth, the tropics would have received the most direct sunlight. While perhaps not enough to melt the main ice sheets, this solar energy could have created localized areas of thinner ice, or perhaps even small temporary patches of open water near the equator. Some climate models support this slushball Earth hypothesis, suggesting the planet wasn't a solid hard freeze, but retained a dynamic, albeit largely frozen, equatorial belt. Within these sunlit patches of thin ice or open water, photosynthetic life, algae and cyanobacteria, might have persisted. These tiny pockets of primary productivity could have supported a limited ecosystem, providing a crucial lifeline for simple eukaryotes through the long glacial winter. Imagine microscopic algae blooming within brine channels in the sea ice itself, or clinging to existence in a fleeting equatorial polynya, an area of open water surrounded by ice. Volcanic islands could have offered another type of sanctuary. Active volcanoes, punching through the ice sheets, would have created localized zones of heat and meltwater. Hot springs associated with this volcanism, both on land and spilling into the surrounding frozen ocean, could have provided warm, nutrient-rich and chemically diverse microhabitats where life might have held on. These volcanic islands would have been like tiny, scattered lifeboats on a vast, frozen sea. Even the ice itself might have served as a refuge. Modern glaciers and sea ice are known to harbour surprisingly diverse microbial communities, living within tiny pockets of liquid water trapped in the ice matrix, or on the surfaces of cryoconite holes, dark, meltwater-filled pits on the glacier surface. Perhaps the hardiest Proterozoic microbes and simple eukaryotes employed similar strategies, surviving within the great ice sheets that covered the planet. And finally, there is the possibility of survival in subglacial lakes. We know today that vast lakes of liquid water can exist beneath miles of ice, like Lake Vostok in Antarctica, kept liquid by geothermal heat and the immense pressure from above. Could similar lakes, hidden beneath the cryogenian ice sheets, have provided stable, long-term refuges for microbial and perhaps even simple eukaryotic life? These potential refuges, deep sea vents, equatorial slush zones, volcanic hotspots, the ice itself, and subglacial lakes highlight life's incredible ability to adapt and endure in the most extreme environments imaginable. They were likely small, isolated pockets scattered across a vast frozen world. But they were enough. They were the biological arcs that carried the precious cargo of eukaryotic evolution through the planetary deep freeze, preserving the potential that would finally blossom when the great thaw arrived and the oceans were once again ready for a new chapter. Life may have clung to existence in scattered refuges beneath the vast cryogenian ice sheets, but the ocean itself, sealed off from the atmosphere and sunlight for millions of years, underwent a profound chemical transformation. The waters trapped beneath the ice became a strange, stagnant, and potentially toxic brew, a chemical landscape vastly different from the Proterozoic seas that preceded the freeze. Understanding this hidden chemistry is crucial to appreciating the challenges faced by the survivors and the unique conditions that awaited life when the great thaw finally came. With the ocean surface sealed by kilometers of ice, the two most fundamental exchanges that govern ocean chemistry were largely shut down. First, the exchange of gases with the atmosphere ceased. Oxygen, produced perhaps in tiny amounts by microbes living within the ice or in fleeting equatorial open water, could not easily penetrate the vast, dark water mass below. At the same time, gases building up within the ocean, released perhaps by volcanic activity or microbial metabolism, could not easily escape into the sky. The ocean became a sealed chemical reactor. Second, the input of sunlight was extinguished. Photosynthesis, the great engine that drives primary productivity and oxygen production in the surface ocean, effectively stopped, except perhaps in those hypothetical thin ice or open water refuges near the equator. The base of the marine food web was plunged into darkness. In this dark, sealed-off world, oxygen levels likely plummeted throughout the vast majority of the ocean volume. Any remaining oxygen would have been consumed by the slow decomposition of organic matter raining down from above, perhaps originating from life, within the ice, or by chemosynthetic processes near the seafloor. The ocean beneath the ice likely became overwhelmingly anoxic, returning to a state reminiscent of the much earlier Archean Eon, and in the absence of oxygen, other chemical processes would have taken over. Bacteria that thrive in anoxic conditions would have flourished. Some of these perform anaerobic respiration using substances like sulfate SO42- instead of oxygen to break down organic matter. A key byproduct of sulfate reduction is hydrogen sulfide, H2S, that toxic, rotten egg-smelling gas. It is highly probable that vast portions of the deep ocean beneath the snowball ice became euxinic, saturated with poisonous hydrogen sulfide. This would have made the deep sea utterly lethal for any oxygen-dependent eukaryotic life that might have survived the initial freezing. At the same time, the chemistry of essential nutrients would have shifted dramatically. Without active biological cycling in the sunlit surface waters, and perhaps with increased input from subglacial volcanic activity or weathering beneath the ice sheets, certain elements might have accumulated to unusual concentrations in the trapped seawater. Dissolved iron, largely removed from the oceans during the Great Oxidation event, might have begun to build up again in the anoxic depths, released from hydrothermal vents or leached from sediments. Phosphorus, a key nutrient for life, might also have accumulated, unable to be fully consumed by the light-starved primary producers. Imagine this hidden ocean, dark, cold, though liquid, under immense pressure, largely devoid of oxygen, potentially rich in toxic hydrogen sulfide and dissolved metals like iron. It sounds like an utterly hostile environment. Yet, paradoxically, this strange chemical state might have held the seeds of future abundance. The accumulation of nutrients like phosphorus in the deep, trapped waters created a vast, untapped reservoir of fertility. When the Great Thaw eventually came and ocean circulation restarted, this immense reservoir of deep ocean nutrients would be brought suddenly and dramatically to the surface. This massive planetary-scale upwelling of nutrients is thought to be one of the key factors that fueled the explosion of algal life, the subsequent rise in oxygen, and ultimately the emergence of the first large complex animals in the Ediacaran period that followed. The frozen ocean of the Cryogenian was a chemical pressure cooker, slowly accumulating stress, toxins, and nutrients in its dark, isolated depths. The ice acted as a lid, holding the system in a state of suspended animation. But when that lid finally melted, the contents would erupt, chemically transforming the global ocean and setting the stage for the next, long-awaited chapter in the story of life. The deep freeze could not last forever. The Earth's internal heat engine continued its relentless work. Volcanoes, punching through the immense ice sheets, continued to vent gases into the atmosphere, patiently, relentlessly, over millions of years. The primary gas among them was carbon dioxide. Sealed beneath a reflective, icy shell, the planet's normal climate regulation systems were offline. The CO2 simply accumulated in the atmosphere, higher and higher, building an invisible greenhouse blanket above the frozen world. Eventually, inevitably, a tipping point was reached. The concentration of CO2 became so immense, perhaps hundreds of times higher than modern levels, that the resulting greenhouse effect finally became strong enough to overwhelm the reflectivity of the ice. The planet began to warm. The Great Thaw, marking the end of the Cryogenian period around 635 million years ago, may have been geologically swift, perhaps unfolding over mere thousands of years. A blink of an eye compared to the millions of years of deep freeze. But its impact on the planet was profound, violent, and utterly transformative. Imagine the scene. The colossal ice sheets, miles thick, begin to melt under a rapidly warming sky. Not a gentle spring thaw, but a hothouse deluge. Rivers of meltwater, far larger than any rivers on Earth today, carve immense channels across the continents, carrying staggering volumes of pulverized rock and sediment towards the sea. Glaciers retreat, carving off continent-sized icebergs into the awakening oceans. Sea levels rise dramatically as the water locked away in the ice returns to the liquid world. The sheer volume of fresh water pouring off the melting continents would have dramatically altered ocean salinity and circulation. The sudden influx of cold, fresh meltwater might have temporarily disrupted ocean currents, creating complex patterns of layering and mixing. And crucially, that immense load of glacial sediment, rock ground into fine powder by the moving ice over millions of years, was dumped unceremoniously into the oceans. This sediment was incredibly rich in nutrients, particularly phosphorus, which had been scoured from the continents by the glaciers. At the same time, the intense greenhouse conditions, fueled by those massive CO2 levels, likely led to hyper-accelerated rock weathering on the newly exposed land surfaces. Warm temperatures and perhaps intense rainfall, driven by the high CO2, would have rapidly broken down rocks, leaching even more nutrients, including phosphorus and essential trace metals, into the rivers and ultimately into the sea. The oceans, recently starved and stratified beneath the ice, were suddenly hit by a nutrient tsunami. The surface waters became saturated with the building blocks needed for life, and life responded. The photosynthetic microbes, the cyanobacteria, and the simple eukaryotic algae that had survived in those hidden refuges found themselves in a world reborn. Warm sunlight, abundant nutrients. It was an invitation to bloom on an unprecedented scale. Vast algal blooms, perhaps global in extent, likely turned the surface oceans into thick, green soups. This explosion of primary productivity had a profound consequence. Oxygen. Photosynthesis releases oxygen. This massive post-glacial bloom would have pumped enormous quantities of oxygen into the surface waters and the atmosphere above. This is thought to be the trigger for the second great oxygenation event in Earth's history, the event that finally raised oxygen levels high enough and stably enough to support the evolution of large, complex, multicellular animals. But the aftermath wasn't entirely positive. The sheer amount of organic matter produced by these blooms raining down into the depths would have fueled intense decomposition, potentially creating or expanding anoxic zones in the midwaters even as the surface became oxygenated. The ocean chemistry remained complex and perhaps unstable. And finally, as the oceans absorbed the immense atmospheric CO2, another chemical process took place. The dissolved carbon dioxide reacted with the abundant calcium ions washed in from the weathered continents, leading to the rapid precipitation of thick layers of carbonate rock directly on top of the glacial deposits. These distinctive cap carbonates are the geological exclamation point marking the end of the snowball Earth events worldwide. The Great Thaw was more than just a warming. It was a violent chemical and biological reset. It flushed the oceans with nutrients, triggered an oxygen revolution, and deposited unique geological signatures. It transformed the planet from a frozen wasteland into a fertile, oxygenated, and radically different world. The long Proterozoic quiet was definitively over. The stage was finally truly set for the Ediacaran enigma. The snowball Earth, that profound planet-encompassing deep freeze, stands as one of the most dramatic and extreme chapters in our planet's entire 4.5 billion-year history. Yet, for all its immense significance, the Cryogenian period and the strange, frozen oceans that defined it remain relatively obscure in our popular understanding of the deep past. It is a truly forgotten winter. Why? Perhaps because its signature is written less in the charismatic forms of giant fossils and more in the subtle language of geochemistry, in isotopic ratios hidden within ancient rocks, and in the strange, seemingly out-of-place layers of glacial debris found even in ancient tropical latitudes. It requires a different kind of geological detective work to even comprehend its scale and existence. Perhaps, too, the sheer improbability of it makes it difficult to grasp. The idea of our entire blue planet turning into a white snowball feels more like speculative fiction than geological fact. It challenges our intuitive sense of planetary stability. And yet, the evidence is compelling, gathered painstakingly over decades from rocks around the world. The unique glacial deposits, the strange cap carbonates that follow them, the dramatic isotopic shifts, they all point towards a time, or perhaps multiple times, when ice ruled the world on an unprecedented scale. The oceans of this era, Mirovia fragmenting beneath the ice, the nascent Adamastor and Mozambique basins frozen at birth, the early Panthalassa sealed from the sky, represent a unique and crucial phase in Earth's hydrohistory. They were oceans under siege, transformed into dark, cold, largely breathless realms. They were the ultimate test of life's resilience. To contemplate these frozen seas is to contemplate life reduced to its barest essentials, clinging to existence in the most marginal of refuges. It forces us to reconsider the boundaries of habitability, the incredible tenacity of the evolutionary spark, and crucially, the cryogenian oceans were not just a passive interlude, they were an active crucible. The extreme conditions, the global ice cover, the altered ocean chemistry, The profound isolation of potential refugees likely acted as powerful evolutionary drivers. Perhaps the intense environmental stress selected for new adaptations, new levels of cellular cooperation, new genetic innovations within the surviving eukaryotic lineages. Perhaps the very act of surviving the snowball somehow primed life for the great explosion of complexity that was to follow. The subsequent thaw, unleashing the stored nutrients and triggering the second great rise of oxygen, was the direct consequence of this immense glacial period. The Cryogenian wasn't just an interruption, it was the necessary, albeit brutal, precondition for the Ediacaran and Cambrian worlds. It was the harsh winter that paved the way for the evolutionary spring. So, while these frozen oceans may lack the charismatic megafauna of later eras, while their story is told in the subtle language of isotopes rather than the dramatic shapes of bones, their importance cannot be overstated. They represent a critical turning point, a planetary near-death experience from which life emerged, transformed, and ready to embark on its greatest adventure yet, the invention of the animal kingdom. As we leave this forgotten winter behind and move forward into the slightly warmer and infinitely stranger waters of the Ediacaran period, we carry with us the understanding that the stage for life's first great flowering was prepared in the crucible of its deepest ice age. The silence of the snowball was the prelude to the first enigmatic garden. Our journey continues forward, leaving the dramatic freeze-thaw cycle of the Cryogenian and the enigmatic dawn garden of the Ediacaran behind. We emerge into a new geological period, the Ordovician, beginning roughly 485 million years ago. This is a time often overshadowed by the Cambrian explosion that preceded it, yet it represents an equally profound, though perhaps subtler, revolution in marine life. The basic animal body plans established in the Cambrian now began to diversify, specialize, and build ecosystems of a complexity never before seen. This was the Great Ordovician biodiversification event, and it filled the oceans with a cast of characters both strangely familiar and deeply alien. The world itself continues its slow reconfiguration. The fragments of the Rodinia supercontinent are still drifting. Laurentia, ancient North America, Baltica, Northern Europe, and Avalonia, Western Europe, Eastern North America, are converging, slowly closing the ancient Iapetus Ocean that lies between them. Further south, Gondwana remains a vast continental mass, but smaller pieces are rifting away, opening new oceanic gateways like the nascent Rhyic Ocean. Other, smaller, and now long-vanished seaways like the Tornquist Sea between Baltica and Avalonia, and the Ural and Khanty Oceans separating Baltica from Siberia, carve complex patterns across the globe. Global climates are generally warm, perhaps reaching hothouse conditions at times. Sea levels are exceptionally high, creating vast, shallow continental shelves, epicontinental seas, bathed in sunlight. These warm, shallow waters become the crucibles of Ordovician life. Imagine descending into these seas. The murky ambiguity of the Ediacaran is gone. The water is clearer, perhaps, and the seafloor is teeming with visible, structured life. The Cambrian experiments have given way to established dynasties. The trilobites, survivors from the Cambrian, are still incredibly abundant and diverse, scuttling across the seabed in 1,000 different forms. But they are no longer the only major players. Everywhere you look, the seafloor is encrusted, carpeted, almost paved with shelled creatures. These are primarily the brachopods, filter feeders whose two-part shells dominate the fossil record of this era. Joining them are early bivalves, clams, and gastropods, snails, beginning their long evolutionary ascent. And rising above this shelled pavement are intricate, three-dimensional structures. Not yet the great coral reefs of later times, but impressive reefs nonetheless, built by communities of calcareous sponges, strange tabulate and rugose corals, early extinct coral groups, abundant bryozoans, and calcareous algae. These reefs create complex habitats bustling with hidden life. Elegant crinoids, the sea lilies, form dense meadows on the seafloor, their feathery arms filtering the plankton-rich waters. Strange, extinct echinoderms like cystoids and blastoids add to the diversity of these underwater gardens. The water column itself is becoming more active. While fish are still relatively primitive, mostly jawless, armored bottom dwellers, the first jawed fish are beginning to appear, hinting at the revolution to come. The eurypterids, or sea scorpions, continue to prowl, some achieving formidable sizes. And dominating the open water as the apex predators are the creatures we met earlier, the cephalopods, particularly those colossal straight-shelled orthocones. This Ordovician world is instantly recognizable as a complex marine ecosystem. It has clear producers, herbivores, filter feeders, and predators. It has structure, diversity, and intricate ecological relationships. And yet it is profoundly different from a modern ocean. The overwhelming ecological dominance belongs not to the swift-moving fish or the complex crustaceans we know today, but to sessile, bottom-dwelling filter feeders, creatures that simply sat in one place, patiently straining tiny particles of food from the water. This gives the Ordovician Sea a unique character, a different rhythm. It was, in many ways, the great age of the filterers, a kingdom built on patience and the richness of the water itself. And the most prominent architects of this kingdom, besides the reef builders, were organisms that built cities out of shells. When we think of marine reefs today, our minds immediately conjure images of vibrant, colourful coral gardens teeming with fish. Corals, those small polyps building vast, stony cities through colonial cooperation, are the undisputed masters of modern reef construction. But the reef-building guild has changed players throughout Earth's history. The Ordovician period, while witnessing the rise of the first truly massive reef ecosystems, built its underwater metropolises using a different, stranger, and largely forgotten cast of architects. Descend again into that warm, shallow Ordovician Sea. The most striking structures rising from the seafloor are the reefs, creating complex topographies, islands of intense biological activity. But look closely. These are not the familiar branching or brain-like shapes of modern scleractinian corals. A dominant group of builders belongs to the sponges, not the soft, squishy sponges you might imagine, but stony, calcareous forms. Chief among them were the stromatoporoids. Imagine massive, layered, stony structures, growing upwards and outwards, sometimes forming immense domes or thick, encrusting pavements that could cover vast areas. Their internal structure was a complex network of canals and pillars, housing the living sponge tissue that filtered vast quantities of water. Stromatoporoids were incredibly successful, forming the very framework of many Ordovician reefs, fulfilling the same ecological role that stony corals do today. Alongside them, another enigmatic group contributed significantly, the receptaculatids. These organisms, sometimes called sunflower corals, though they weren't corals at all, built strange, geometrically patterned skeletons. Imagine a shallow, bowl-shaped or plate-like structure, its surface covered in a precise hexagonal or diamond pattern of plates, looking almost like a fossilized pineapple slice or a complex mineralized sunflower head. Their exact biological affinity remains debated, perhaps related to algae, perhaps sponges, but their distinctive patterned skeletons were a common and robust component of these ancient reefs. Early, now extinct groups of corals were also present, though perhaps playing a supporting role rather than dominating. The tabulate corals formed colonies of tightly packed, slender tubes, often creating honeycomb-like structures or delicate branching forms. The rugose corals, sometimes called horn corals, often grew as solitary horn-shaped individuals, though some also formed colonies. While recognizable as corals, their internal structure and growth forms were distinctly different from the corals that would evolve after the Permian extinction, and binding this entire structure together, acting as the mortar between the larger stony bricks, were the bryozoans, moss animals, and calcareous algae. Bryozoans formed delicate, intricate, fan-like or encrusting colonies composed of thousands of microscopic individuals working together. Calcareous algae, like primitive coralline algae, deposited calcium carbonate within their tissues, helping to cement the reef structure and contribute to its bulk. This consortium, the massive stromatoporoid sponges, the patterned receptaculitids, the early tabulate and rugose corals, cemented by bryozoans and algae, created reefs of immense scale and complexity. They provided the essential three-dimensional habitat, the nooks and crannies, the sheltered lagoons, that allowed an explosion of other life forms to thrive. These Ordovician reefs were ecological dynamos. They were hotspots of biodiversity, sheltering countless species of trilobites, brachiopods, gastropods, crinoids, and the first primitive fish. They were dynamic systems, constantly growing, competing for space, and responding to changes in sea level and water conditions. They represent a different solution to the engineering challenge of building a reef, a different assemblage of architects using different biological blueprints. They are a forgotten underwater architecture, monuments built by lineages now largely extinct or relegated to minor roles. Yet for tens of millions of years, these sponge bryozoan algal reefs dominated the shallow seas, creating the vibrant, bustling heart of the Ordovician marine world, a world utterly dependent on the patient, filter-feeding life that encrusted every available surface. While the ancient reefs built by sponges and bryozoans formed the towering cities of the Ordovician seas, the vast plains surrounding them, the seemingly endless stretches of the shallow seafloor, were dominated by another group, carpeting the substrate in numbers almost too vast to comprehend. If the Ordovician was the age of filter feeders, then its undisputed emperors were the brachiopods. To the untrained eye, a fossil brachiopod might look almost indistinguishable from a clam or a mussel. It possesses two hard calcium carbonate shells, hinged together, enclosing a soft body within. But this resemblance is purely superficial, a classic case of convergent evolution finding similar solutions to similar problems. Brachiopods belong to a completely separate phylum of life, with a fundamentally different internal anatomy and evolutionary history. Their key distinguishing feature lies within. Instead of the muscular foot used by clams for burrowing, a brachiopod possesses a complex, delicate, and beautiful feeding structure called a lophophore. This is an intricate, often coiled or spiraled crown of ciliated tentacles, which it uses to generate water currents and filter microscopic food particles from the surrounding sea. They are suspension feeders, pure and simple, patiently straining the ocean's thin soup for sustenance. Many brachiopods also possess a fleshy stalk or pedicle emerging from a small opening in one of their shells, which they use to attach themselves firmly to the seafloor, to rocks, or even to the shells of their neighbors. And in the Ordovician period, they achieved an ecological dominance that is difficult to overstate. They exploded in diversity, evolving thousands of species adapted to virtually every shallow marine environment. Their fossilized shells are often the most abundant macroscopic fossils found in Ordovician rocks worldwide, sometimes forming thick limestone beds composed almost entirely of their tightly packed remains. Visualize the Ordovician sea floor away from the main reef structures. It is not bare mud or sand. It is a living pavement, a dense carpet woven from millions upon millions of brachiopod shells. Different species partition the space, small, delicate forms nestled in crevices, larger, robust species forming dense clusters on exposed surfaces, perhaps strange, spiny varieties adapted to softer sediments. They create their own, low-lying, complex habitat. The sheer density of their shells provides surfaces for algae and bryozoans to colonize. The small spaces between them offer refuge for tiny worms, crustaceans, and juvenile trilobites. They are not just inhabitants of the ecosystem, they are the ecosystem, forming the very fabric of the shallow benthic world. Their success speaks to the conditions of the Ordovician seas. The warm, shallow, nutrient-rich waters, perhaps teeming with plankton, provided the perfect environment for these efficient, sessile filter feeders. And perhaps the relative scarcity of shell-crushing predators, compared to later eras, allowed them to flourish with minimal pressure. Life as a brachiopod was one of profound stillness. Attached to the seabed, encased in its protective shell, its existence was a slow, patient, and constant act of filtering, drawing life directly from the water flowing past. They were the quiet, unassuming, yet overwhelmingly successful foundation of the Ordovician marine world. Their dominance would persist for much of the Paleozoic era. Though challenged by the rise of the bivalves, clams and their relatives, brachiopods remained major players until the Great Dying at the end of the Permian, which they barely survived. Today, they are reduced to just a few hundred species, mostly confined to deeper, colder waters, a mere shadow of their former glory. But here, in the Ordovician, their kingdom was absolute. These forgotten shells, weathering out of limestone hills and road cuts around the world, are the silent testament to an age when the seafloor belonged to the lophophore, a time when life thrived through the simple, patient act of filtering the ancient sea. And suspended gracefully above these shelled carpets, another group of filter feeders added a different kind of beauty to the underwater landscape. Rising gracefully above the shell-paved floor and the low-lying frameworks of the ancient reefs, another group of filter feeders added a different kind of architecture, a vertical dimension of delicate elegance, to the Ordovician and Silurian seas. These were the crinoids, the creatures commonly known as sea lilies. Despite their plant-like appearance, crinoids are not plants at all. They are animals belonging to the phylum Echinodermata, the same group that includes modern starfish, sea urchins, and sea cucumbers. Their bodies exhibit the characteristic five-fold radial symmetry of their relatives, though often modified into intricate, feathery structures. Envision a shallow Ordovician sea floor bathed in dappled sunlight filtering through the water. Growing in dense clusters resembling fields of strange underwater flowers are the crinoids. The most common form in this era was the stalked crinoid, anchored firmly to the seabed by a root-like structure called a holdfast. A long segmented stalk rises upwards into the water column. This stalk, composed of numerous stacked, disc-like plates of calcium carbonate, ossicles, could be short or incredibly long, sometimes reaching many meters in height in later periods. At the top of this stalk sits the main body of the creature, the calyx, a small, cup-shaped structure housing its internal organs, and extending upwards and outwards from this calyx are the arms. These arms, typically 5 in number but often branching multiple times to create a dense crown, are lined with delicate feathery appendages called pinnules. This entire, intricate crown of arms and pinnules is the crinoid's feeding apparatus. It is a living, three-dimensional filter basket. The creature orients its crown into the prevailing current. Tiny tube feet lining the pinnules secrete mucus, trapping microscopic plankton and particles of organic detritus drifting by. Cilia, tiny beating hairs, then transport this captured food down grooves along the arms, leading eventually to a central mouth located within the calyx. Life for a stalked crinoid was one of serene, passive suspension. Anchored in place, it simply let the ocean bring its meals, its feathery arms a beautiful, efficient net woven to catch the faintest whispers of sustenance. During the Ordovician and Silurian periods, these crinoids experienced a major evolutionary radiation, becoming incredibly diverse and abundant. Vast meadows or gardens of sea lilies covered enormous areas of the seafloor, their tall stalks and feathery crowns creating a unique, multi-layered habitat. Different species evolved different stalk lengths, different arm structures, perhaps specializing in filtering food from specific levels within the water column, partitioning the resources like trees of varying heights in a forest. Their fossilized remains are a testament to their abundance. The individual disc-like plates, ossicles, that made up their stalks and arms are among the most common fossils found in Paleozoic rocks worldwide, sometimes forming thick limestone beds known as crinoidal limestones. Occasionally, entire articulated crinoid crowns and stalks are preserved, offering breathtaking glimpses of their delicate, flower-like beauty. These underwater gardens, swaying gently in the ancient currents, would have added another layer of complexity to the Ordovician ecosystem. They provided shelter for smaller creatures amidst their stalks. Their presence altered water flow patterns near the seabed, and upon their death, their calcium carbonate skeletons contributed significantly to the formation of sedimentary rock. Like the brachopods, the stalked crinoids were masters of the filter-feeding lifestyle, perfectly adapted to the plankton-rich waters of the early Paleozoic. While some lineages survive today, often in deeper waters, and their free-swimming relatives, the feather stars, are still common, the sheer abundance and dominance of the great stalked crinoid meadows faded after the Paleozoic era. But here, in the forgotten oceans of the Ordovician and Silurian, they stood in their silent, feathery glory, elegant counterpoints to the shelled pavements below and the stony reefs nearby, embodying the patient, filter-feeding heart of this ancient marine world. Yet, this world of passive filterers was not without its dangers. New kinds of predators were emerging, testing the defenses of this established order. This world we have painted, a world of stationary reef builders, carpets of shelled filter feeders, and gardens of feathery sea lilies, might sound almost idyllic, a slow, peaceful kingdom dominated by passive grazers of the water column. But no ecosystem, no matter how ancient, is entirely without its dangers. Predation, that great engine of evolutionary arms races, was certainly present in the Ordovician and Silurian seas. However, the predators themselves were different, operating under different rules and possessing different weaponry than the swift sharks and intelligent marine mammals that would rule the oceans later. The undisputed heavyweight champions, the apex predators looming over this entire ecosystem, were the creatures we met earlier, the colossal straight-shelled orthocone cephalopods. Their sheer size, reaching perhaps 30 feet or more, would have placed them at the very top of the food chain. Moving slowly through the water column, these giants likely preyed upon trilobites, eurypterids, and perhaps the early, slow-moving fish, using their powerful tentacles and sharp beaks to dispatch their victims. Their presence cast a long shadow, a constant, albeit slow-moving threat in the upper layers of the ocean. But closer to the seafloor, amongst the reefs and crinoid gardens, other formidable hunters patrolled. Chief among these were the eurypterids, the sea scorpions. While their origins stretch back into the Cambrian, the Ordovician and particularly the Silurian periods saw them diversify and achieve truly terrifying sizes. Imagine creatures like Pterygotus, resembling a colossal aquatic scorpion or lobster, reaching lengths of over 2 meters or 7 feet. They possessed large, powerful, crushing claws and sleek, streamlined bodies, suggesting they were active swimmers, perhaps capable of pursuing prey with surprising speed. They would have been formidable predators of trilobites, early fish, and perhaps even smaller orthocones. And then there were the fish. While the Ordovician was still largely the age of jawless, armored bottom dwellers, the ostracoderms, the crucial evolutionary innovation of jaws was beginning to appear. The first placoderms, bizarre, heavily armored fish with bony plates covering their heads and bodies, and sharp, bony blades acting as primitive jaws, were emerging. Though initially small, these represented a revolutionary new kind of predator, capable of delivering a powerful, slicing bite. Alongside them, the first acanthodians, or spiny sharks, though not true sharks, were experimenting with fins and a more streamlined form, hinting at the future agility of fish. These early jawed fish were likely not yet challenging the dominance of the giant cephalopods or the largest eurypterids, but they represented a new kind of threat, particularly perhaps to smaller, softer-bodied creatures. Their ability to bite, to grasp, to pursue added a new dynamic to the predator-prey relationships. So, the Ordovician and Silurian seas were far from peaceful. There were giants lurking above, powerful clawed hunters patrolling the reefs, and the first hints of toothy, bony predators emerging from the evolutionary shadows. However, the style of predation was likely different. This was still largely a world without the lightning-fast pursuit speeds of modern tuna or sharks. It was a world perhaps dominated by ambush, by slow stalking, by crushing or grasping rather than swift, slicing bites, though the placoderms were changing that. Armor, like that of the trilobites and ostracoderms, was still a highly effective defense. This unique assemblage of predators, the slow cephalopod battleships, the powerful eurypterid cruisers, the early armored fish tanks, helped shape the evolution of life in these forgotten oceans. They applied selective pressure, favoring creatures with better defenses, better escape strategies. But even these formidable hunters belonged to dynasties that would eventually fade, overshadowed by the rise of the more efficient, more adaptable swimmers to come. Their presence reminds us that even in this seemingly tranquil kingdom of filter feeders, the ancient dance of hunter and hunted was playing out its slow, patient, and sometimes brutal choreography. And the very success of this entire ecosystem, this specific way of life, made it vulnerable to the larger planetary changes brewing on the horizon. For nearly 90 million years, spanning the Ordovician and Silurian periods, this unique marine world thrived. It was an age defined by sprawling sponge bryozoan reefs, seafloors paved with brachiopods, gardens of swaying crinoids, and ruled from above by colossal orthocones and formidable sea scorpions. It was a time of immense biological productivity, evolutionary innovation, and ecological complexity. And yet, when we tell the grand story of prehistoric oceans, this entire chapter often receives only a passing mention. It is frequently overshadowed, relegated to a mere prelude before the arrival of what is often perceived as the main event. Why are these Ordovician and Silurian seas, teeming with such strange and successful life, so often forgotten? Part of the answer lies, perhaps, in the very nature of its dominant inhabitants. Brachiopods, crinoids, stromatoporoid sponges, orthocone cephalopods. These names do not resonate in the popular imagination like Tyrannosaurus rex or Megalodon. They lack the immediate charisma, the visceral appeal of giant predators with teeth and claws, or the relatable familiarity of creatures closer to our own lineage. They represent ancient, often extinct branches of the tree of life, forms that feel distant, alien, difficult to connect with emotionally. They are the quiet, shelled architects and filterers, easily overlooked in a story often drawn to the dramatic and the predatory. Furthermore, the very success and stability of this filter-feeding kingdom might contribute to its perceived obscurity. The Cambrian explosion that preceded it, captures our imagination with its sheer, explosive novelty, the sudden appearance of almost all animal body plans. The Devonian period that followed is famed as the Age of Fishes, witnessing the spectacular rise and diversification of vertebrate life in the water, including the first steps onto land. Caught between these two revolutionary moments, the long Ordovician-Silurian interval can sometimes feel like a stable, perhaps less transformative, plateau. And it is precisely the shadow of those fish that looms largest over the memory of this era. The Devonian period saw the true conquest of the oceans by jawed vertebrates. Placoderms achieved monstrous sizes, sharks evolved into sophisticated predators, and the bony fish embarked on the trajectory that would lead to their overwhelming dominance today. In the grand narrative focused on vertebrate evolution, our own story ultimately, the rise of fish becomes the central plot point, and the preceding era, despite its own richness, is often reduced to simply the world before fish truly took over. The ecosystems themselves, while complex, perhaps lacked the sheer visual dynamism we associate with later marine worlds. An ocean dominated by sessile filter feeders might seem, to our modern eyes, less active, less exciting than a bustling coral reef filled with darting fish or a Mesozoic sea patrolled by giant marine reptiles. Finally, the geological legacy can be subtle. While fossils like brachiopod shells and crinoid stems are incredibly common, forming vast limestone deposits, they often lack the immediate awe-inspiring impact of a complete dinosaur skeleton or a giant shark tooth. Reconstructing the intricate beauty of a crinoid garden or the full scale of an orthocone requires more scientific interpretation, more imaginative effort. Yet, to dismiss these forgotten oceans as merely a quiet interlude is to miss a crucial chapter in the story of life. This was the time when the fundamental structure of modern marine ecosystems was first established. It was the age when reefs became major planetary players. It was the period that saw the refinement of early animal body plans and the establishment of complex food webs. And it hosted dynasties, like the orthocones, that achieved a scale and dominance unparalleled in their time. The Ordovician and Silurian seas were not a prelude. They were a distinct and magnificent world in their own right. Their inhabitants may be less famous, their dramas quieter, but their legacy is written in the very fabric of the Paleozoic era. They are a reminder that the story of life is not just about the loudest players or the most familiar forms, but also about the silent architects, the patient filterers, and the forgotten kingdoms that paved the way for all that followed. Our final voyage takes us much closer to our own time, though still separated by an immense gulf of millions of years. We leap forward past the age of giant amphibians, past the rise and fall of the synapsids, past the entire reign of the dinosaurs' earliest ancestors, and plunge into the heart of the late Cretaceous period, roughly 100 to 70 million years ago. This is a world dramatically different from the ancient Paleozoic seas we have just left. The supercontinent of Pangaea, which dominated the Permian and Triassic, has long since fragmented. The continents are drifting towards their modern positions, opening vast new ocean basins like the young Atlantic. Dinosaurs rule the land with undisputed authority. Tyrannosaurus prowls what will become North America. Titanosaurs lumber across South America. Duck-billed hadrosaurs browse in vast herds across Asia. And the global climate is once again in a state of extreme warmth. This is perhaps the peak of the Mesozoic greenhouse world. Temperatures are significantly higher than today. There are no polar ice caps. Consequently, sea levels are extraordinarily high, perhaps hundreds of feet higher than they are now. This dramatic rise in sea level had a profound effect on the geography of the continents. Vast areas of low-lying land were flooded, creating shallow, warm epicontinental seas that penetrated deep into the hearts of the land masses. Europe was largely an archipelago, Africa was split by seaways, and nowhere was this inundation more spectacular or more transformative than in North America. For millions of years during the late Cretaceous, a vast, shallow inland sea stretched all the way from the Arctic Ocean in the north down to the Gulf of Mexico in the south. It effectively split the entire North American continent into two massive islands: Laramidia to the west, containing the future Rocky Mountains, Alaska, and down to Mexico, and Appalachia to the east, covering the eastern seaboard. This immense body of water, known to geology as the Western Interior Seaway, was a truly remarkable feature. It was thousands of miles long, perhaps 600 miles wide at its greatest extent, yet relatively shallow, likely no more than 600 feet deep in most places, and perhaps much shallower towards its fluctuating shorelines. Imagine looking out across this seaway. You see not the crashing waves of an open ocean, but perhaps calmer waters stretching to a hazy horizon. The climate is subtropical to tropical, warm, humid. The shores are lined not with sandy beaches, but perhaps with dense, mangrove-like swamps or forests of primitive flowering plants and conifers extending right down to the water's edge. This seaway was not a static feature. Its shorelines advanced and retreated over millions of years as global sea levels rose and fell slightly, and as tectonic forces continued to shape the continent. It was a dynamic, shifting, inland ocean, a temporary aquatic world superimposed onto the heart of a continent. And for the millions of years it existed, the Western Interior Seaway became its own unique ecosystem, a vast, warm, shallow incubator for marine life. Cut off to some extent from the open oceans, yet connected at its northern and southern ends, it developed its own distinctive cast of characters. It became a haven for giant marine reptiles, bizarrely shaped ammonites, and colossal shellfish. This lost inland sea, though geologically fleeting compared to the great ocean basins, represents another fascinating, forgotten ocean, a world that existed for a significant chapter of Earth's history, profoundly shaping the evolution of life in North America, only to vanish completely as the continents rose and the waters retreated. Its story is written in the chalks and shales of the American Midwest, a testament to a time when Kansas was beachfront property and monsters patrolled the inland sea. The warm, shallow, and incredibly productive waters of the Western Interior Seaway did not remain empty for long. They quickly became the hunting ground for some of the most formidable marine predators the planet has ever known. While sharks certainly patrolled these waters, and giant predatory fish like Zephactinus, a fanged monster reaching lengths of 20 feet, posed their own threat, the true apex predators, the undisputed rulers of this inland sea, belonged to a different lineage entirely. They were reptiles returned to the water with a vengeance, and chief among them were the mosasaurs. Imagine a creature that embodies the predatory power of a shark, the serpentine flexibility of a snake, and the sheer scale of a whale, all wrapped in a reptilian form. Mosasaurs were not dinosaurs. They were essentially giant marine lizards, closely related to modern monitor lizards and snakes that had adapted spectacularly to an aquatic life during the late Cretaceous. And the Western Interior Seaway was their heartland. Picture one emerging from the hazy, sunlit depths. A colossal creature, perhaps a Tylosaurus or a Mosasaurus hoffmanii, the largest of their kind, reaching lengths of up to 50 feet or 15 meters, longer than a school bus. Its body is streamlined, powerful, propelled through the water not by paddling limbs, but by broad, powerful tail flukes, similar to those of a shark, delivering immense thrust with each slow side-to-side beat. Its limbs have transformed into paddle-like flippers, used perhaps more for steering and stability than for propulsion. Its head is huge, reptilian, with massive jaws lined with rows of sharp, conical teeth, perfectly designed for seizing and holding struggling prey. And perhaps most unsettlingly, they possessed a second inner row of teeth on their palate, pterygoid teeth, which helped prevent slippery prey from escaping their grip as they swallowed it whole. These were not gentle filter feeders or slow-moving grazers. Mosasaurs were active, powerful predators, occupying the very top of the food web in the seaway. What did they eat? The fossil evidence suggests the answer was simple: anything they could catch. Their fossilized stomach contents reveal a diet that included large fish, like Xiphectinus, sharks, ammonites, their shells sometimes found crushed, within mosasaur gut contents, smaller marine reptiles, and even seabirds, like Hesperornis, that might have rested on the water's surface. They were opportunistic hunters, capable of tackling a wide variety of prey with their sheer size and power. How did they hunt? Unlike the deep-diving ichthyosaurs of earlier times, mosasaurs were likely creatures of the upper water column, perfectly adapted to the relatively shallow depths of the western interior seaway. Perhaps they used ambush tactics, lurking near the seabed and erupting upwards to snatch unsuspecting prey silhouetted against the surface light. Or perhaps they were capable of sustained pursuit, their powerful tails driving them through the water at considerable speed, chasing down schools of fish or slower-moving reptiles. Their presence would have cast a constant shadow of danger over the seaway. Smaller creatures would have lived in perpetual fear of these immense marine lizards. Even the sharks, formidable predators in their own right, were likely prey for the largest mosasaurs. They were the T-Rex of this inland ocean, the ultimate expression of reptilian dominance in the marine realm during the final stages of the Cretaceous. Their fossils, found abundantly in the chalks and shales deposited by the seaway across the American Midwest, paint a picture of a predator perfectly and terrifyingly adapted to its shallow, warm, and productive world. They were the undisputed kings of this forgotten ocean, ruling with brute force and powerful jaws. But they were not the only reptilian giants sharing these waters. Another, equally strange and perhaps more elegant lineage patrolled the depths alongside them. While the powerful brute force of the mosasaurs likely dominated the predatory landscape of the western interior seaway, another, equally successful, though perhaps more enigmatic, group of marine reptiles shared these warm, shallow waters. These were the plesiosaurs, creatures whose strange and unique body plan has captured the human imagination for centuries, sparking legends of sea serpents and lake monsters. Imagine a creature fundamentally different from the streamlined, lizard-like mosasaur. The plesiosaurs came in two main varieties, but the most iconic, the long-necked forms, plesiosauromorphs, presented a truly bizarre silhouette. Picture a large barrel-shaped body, perhaps the size of a small whale. Propelling this body through the water were not powerful tail flukes, but four immense paddle-like flippers, operating with a unique underwater flying motion, similar perhaps to that of a modern sea turtle or penguin. And extending from this robust body, often dwarfing it in length, was an incredibly long, slender, and flexible neck, ending in a disproportionately small head armed with sharp, interlocking teeth. Creatures like Elasmosaurus, one of the most famous inhabitants of the western interior seaway, pushed this design to its extreme. Elasmosaurus itself might have reached lengths of over 40 feet or 12 meters, but an astonishing half of that length was pure neck, composed of over 70 individual vertebrae, 10 times the number in your own neck, granting it incredible flexibility. What was the purpose of this extraordinary anatomy? Unlike the mosasaurs, which seemed built for power and speed, the plesiosaurs, particularly these long-necked forms, appear to have been slower, perhaps more deliberate hunters. Their small heads and relatively weak jaws suggest they were not tackling large, struggling prey. Instead, that incredible neck was likely a specialized tool for ambush and precision hunting of smaller, quicker victims. Imagine an elasmosaurus gliding slowly through the slightly murky waters of the seaway, its large body remaining submerged and relatively inconspicuous below. Its long, serpentine neck, however, could extend far upwards, allowing its small head to stealthily approach unsuspecting schools of fish or squid swimming near the surface. The prey, perhaps focused on dangers from below or the sides, might never even notice the small head approaching slowly from above until the final, lightning-fast, sideways snap of the jaws. The neck acted like a living fishing line, decoupling the predator's large, visible body from the point of attack. It allowed the plesiosaur to hunt in 3 dimensions, striking from unexpected angles, using stealth and reach rather than brute force. Those numerous, needle-sharp interlocking teeth were perfectly designed for snagging small, slippery fish and cephalopods. The western interior seaway, with its abundant schools of fish and ammonites, was an ideal hunting ground for these specialized predators. Fossils of long-necked plesiosaurs are common finds in the same deposits that yield mosasaurs, suggesting these two very different reptilian giants successfully coexisted, perhaps targeting different types of prey or employing different hunting strategies, thereby avoiding direct competition. The image of these creatures, the immense, 4-flippered bodies moving with a slow, powerful grace through the water, their impossibly long necks weaving snake-like through the currents, small heads scanning for prey, is both elegant and deeply alien. They were the long-necked ghosts of this forgotten inland sea, a unique and highly successful evolutionary experiment that thrived for millions of years before ultimately vanishing, along with the mosasaurs and the dinosaurs, at the end of the Cretaceous period. Their fossils remain silent testament to a time when reptiles ruled the waves with forms both terrifyingly powerful and beautifully strange. And beneath these reptilian giants, the seafloor itself hosted its own cast of bizarre and oversized characters. While the great marine reptiles, the mosasaurs and plesiosaurs, commanded the water column of the western interior seaway, the seafloor beneath them, bathed in the warm, shallow, sunlit waters, hosted its own unique and sometimes bizarre community. This was not a world of complex sponge reefs like the Ordovician, nor was it paved with brachopods. Instead, the soft, chalky mud that carpeted the bottom of this inland sea was home to giants of a different kind, shelled creatures that achieved sizes rarely seen before or since, and cephalopods that experimented with forms bordering on the surreal. Perhaps the most astonishing inhabitants of this Cretaceous seabed were the inoceramid bivalves. Imagine a clam. Now imagine a clam that grew not to the size of your hand, or even a dinner plate, but to the size of a car tire, or even larger. This was Inoceramus and its relatives. These colossal, flat clams lay placidly on the soft, muddy bottom, some species reaching diameters of 6 feet or nearly 2 meters across. What allowed these bivalves to achieve such staggering dimensions? The western interior seaway was likely incredibly productive. Nutrients washing in from the surrounding landmasses, combined with the warm, shallow, sunlit conditions, probably fueled massive blooms of plankton, the primary food source for these giant filter feeders. They simply sat on the seafloor, their enormous shells slightly agape, patiently filtering vast quantities of water through their gills, extracting the microscopic bounty that rained down from above. Their immense size might also have offered some protection against predators, though fossil evidence shows that even these giants were sometimes preyed upon, perhaps by specialized mosasaurs or large predatory fish. Their colossal, often rippled shells are common fossils in the chalk deposits of the seaway, silent monuments to a time of incredible marine productivity. Living alongside these placid giants, the ammonites, those ubiquitous coiled cephalopods of the Mesozoic era, were undergoing their own strange final evolutionary flourish in the western interior seaway. While many familiar tightly coiled forms persisted, the late Cretaceous saw the rise of the heteromorph ammonites, creatures that seemed to abandon the neat, orderly spiral of their ancestors and explode into bizarre, uncoiled and seemingly chaotic shapes. Imagine ammonites whose shells started as a tight coil but then straightened out into a long hook like a giant paperclip, scaphites. Picture others forming loose, irregular spirals or even completely straight conical shells, baculites, reminiscent perhaps of their distant orthocone ancestors but belonging to a completely different lineage. Some evolved incredibly complex, almost baroque ornamentation, covered in spines, ribs, and tubercles. What drove this bizarre experimentation in shell shape? Perhaps it was related to changes in lifestyle, adaptations for different modes of swimming or floating. Perhaps it was driven by predation pressure, the strange shapes making them harder for predators like mosasaurs to grasp or crush. Or perhaps it represented a kind of evolutionary overspecialization, a lineage exploring the extremes of its own developmental possibilities just before its final extinction at the end of the Cretaceous. These heteromorph ammonites add another layer of beautiful strangeness to the fauna of the seaway. They represent the final, creative, and somewhat decadent chapter in the long and successful story of the ammonites. Their uncoiled, often fragmented fossils are found alongside the giant inoceramid shells and the bones of the great marine reptiles, completing the picture of a unique and highly specialized ecosystem. The floor of the western interior seaway was a world of giants, giant filter-feeding clams basking in the plankton-rich soup, hunted perhaps by giant marine lizards, while strangely shaped ammonites drifted through the water column like pieces of abstract sculpture. It was a unique assemblage, a fauna perfectly adapted to the specific conditions of this vast, shallow, inland sea. But this sea, born from high global temperatures and rising waters, was a geologically temporary feature. Its time was running out, and its disappearance would erase this entire forgotten ecosystem from the face of the planet. For millions of years, the western interior seaway had teemed with life, a vast, warm, shallow ocean bisecting a continent, hosting giants both reptilian and shelled. It was a unique and vibrant ecosystem, a major feature of the late Cretaceous world, and yet today it exists only in the rock record, in the fossils embedded within the chalks and shales of the North American plains. Why is this immense inland ocean, this world of mosasaurs and giant clams, so often forgotten in the grand narrative of Earth's history? The answer lies, in large part, in its impermanence. Unlike the great deep ocean basins like the Pacific or the Atlantic, which are defined by fundamental plate tectonic boundaries and persist for hundreds of millions of years, the western interior seaway was a geological ephemeron. It was a temporary flood, a consequence of a specific transient set of global conditions. Its existence was tied directly to the high sea levels of the late Cretaceous greenhouse world. The lack of polar ice caps and the overall thermal expansion of the oceans meant that water simply stood higher on the planet, inundating low-lying continental areas. North America, during this time, happened to have a vast, relatively flat interior basin, making it particularly susceptible to this flooding. But sea levels do not remain constant forever. As the Cretaceous period drew to a close, and even more dramatically in the Cenozoic era that followed, the global climate began a long, slow cooling trend. Ice caps began to reform at the poles, water became locked up once again in continental glaciers, and global sea levels began to fall. Simultaneously, tectonic forces were reshaping the North American continent itself. Far to the west, the slow collision of the Pacific plate with the North American plate was in the process of building mountains, the Laramide orogeny, the event that would uplift the Rocky Mountains. This gradual uplift of the western part of the continent began to push the waters of the seaway eastward, squeezing it, narrowing its extent. Imagine this slow geological retreat. Over millions of years, the shorelines of the great inland sea began to recede. What was once a vast open body of water hundreds of miles wide became narrower, shallower. Bays turned into brackish estuaries, estuaries turned into freshwater swamps, and swamps eventually dried out, becoming river valleys and plains. The seaway wasn't drained overnight. It slowly, inexorably withdrew, like a tide going out, never to return. By the early Paleocene epoch, just a few million years after the extinction of the dinosaurs, the western interior seaway was effectively gone. The two halves of North America, Rodinia and Appalachia, were reunited by dry land. The connection between the Arctic and the Gulf of Mexico was severed. An entire ocean had vanished from the map. This relatively short lifespan, perhaps 30 million years in total, a long time by human standards but fleeting geologically, contributes significantly to its forgotten status. It was a spectacular chapter, but a brief one, sandwiched between the rise of the dinosaurs and the rise of the mammals. Furthermore, its inland shallow nature distinguishes it from the great deep oceans that capture our imagination. It lacks the abyssal mystery of the Mariana Trench or the globe-spanning currents of the Pacific. It feels more like a vast, temporary lake than a true ocean, and the life it contained, while spectacular, also largely vanished with it. The mosasaurs, the plesiosaurs, the giant inoceramids, the strange heteromorph ammonites, most of these were creatures highly specialized for the unique conditions of the warm, shallow seaway. When their world disappeared, they disappeared too, either succumbing to the end Cretaceous extinction event or simply losing their habitat as the waters retreated. They left no direct descendants in the modern world to carry their memory forward. The western interior seaway was a magnificent but transient world, a geological footnote perhaps, but one filled with incredible life and high drama. Its legacy lies not in a living ocean, but in the rich fossil beds it left behind, stretching across the heartland of North America, silent testament to a time when giant marine reptiles patrolled the waters above the future wheat fields of Kansas. It is a forgotten ocean precisely because it succeeded, thrived, and then vanished so completely, leaving only its stony ghosts behind. And so, our voyage through the forgotten oceans of prehistoric Earth reaches its final harbor. We have drifted through the steaming chemical soup of the planet's first waters, witnessed the billion-year reign of the microbial seas, felt the crushing silence beneath the snowball ice, navigated the closing passages of the Iapetus between colliding continents, and explored the transient, monster-filled heart of North America's lost inland sea. Each of these oceans, Mirovia, Iapetus, Reich, the western interior seaway, and the countless nameless seas before them, tells a unique story. Each represents a different chapter in the planet's long, fluid, and ever-changing history. They are testaments to the restless power of plate tectonics, the slow but inexorable engine that builds and destroys ocean basins as continents dance across the globe. They are witnesses to the dramatic shifts in climate, from Hadean infernos to cryogenian deep freezes to Cretaceous hothouses, and they were the crucibles within which life itself was forged, tested, and transformed. These oceans are forgotten precisely because they are ephemeral on geological timescales. Unlike the seemingly permanent continents, ocean basins are constantly being created at mid-ocean ridges and destroyed in subduction zones. Their waters shift, their coastlines migrate, their very existence dictated by the slow, grand choreography of the planet. Today's Atlantic is a geological infant compared to the ancient Panthalassa. Today's Mediterranean is merely the last shrinking remnant of the once mighty Tethys. To remember these forgotten oceans is to embrace the profound impermanence of the world we inhabit. It is to understand that the map is never fixed, that the boundaries between land and sea are constantly redrawn by forces far larger than ourselves. But their legacy is not just one of geological change. It is written in the very fabric of life. The unique chemistry of the first oceans may have sparked the origin of life itself. The long, quiet stability of the Proterozoic seas allowed the essential toolkit of complex cellular life to be assembled. The trauma of the snowball Earth oceans triggered the conditions necessary for the rise of animals. The vanished Paleozoic seas hosted the first great experiments in complex ecosystems. And the temporary inland seas of the Mesozoic became incubators for spectacular, specialized faunas. Each forgotten ocean played its part, shaping the trajectory of evolution, filtering life through unique environmental challenges, creating opportunities for new forms to arise. The creatures that inhabited these lost waters, the microbial architects, the giant-shelled cephalopods, the bizarre Cambrian experiments, the mighty marine reptiles, may be gone, but their influence lingers. They are encoded in the DNA of their descendants, embedded in the ecological relationships we see today, and preserved sometimes as ghostly echoes in the silent stone. Perhaps the next time you stand by the shore of a modern ocean, listening to the rhythmic crash of waves, you can imagine the ghosts of these other seas. Imagine the steaming green waters of the Archean. Imagine the ice-locked silence of the Cryogenian. Imagine the straight-shelled giants of the Ordovician, or the mosasaurs patrolling the shallow heart of a vanished continent. The ocean holds the deepest memory of our planet. Its currents are the currents of deep time itself, connecting the distant past to the fleeting present. And within its depths, real or imagined, lies a profound sense of peace, of perspective, of the enduring, resilient, and ever-changing nature of life on Earth. The forgotten oceans may be gone, but their stories flow silently within the waters of the world and within the quiet depths of our own understanding.